Okay, we're at 13.3 concepts of oscillation rates in simple harmonic motion. And before we get to the PowerPoint, I'm actually going to go back to Walter Fent, and this is a demonstration of uniform circular motion. If you remember uh, the oscillating spring pendulum, as it went up and down, the graph uh, showed a sinusoidal form. Well, here's a sinusoidal form generated by an object going around in a circle. And so let's start it. And I'm gonna, I don't know if it's gonna be jerky, so I'm gonna slow it down. But you can see as the circle goes around, you can see that right now the X is at max. It's max. The Y was just 0. Now the X is decreasing and the Y is increasing. So you can see it's a sine wave and a cosine wave side by side. They're just off by 90 degrees, which happens to be the phase relationship between the X and the Y. They are orthogonal. Just for fun, let's look at the velocity. You can see that there's a tangential. I mean, the velocity is tangential, and there is a X component and a Y component. And if you were to follow like the Y component, you would see that it looks like the velocity of the spring going up and down, just the Y. And you could do the same with the X going back and forth this way. Now let's look at the acceleration. Surprise, it's centripetal acceleration. It's going down towards the center. The acceleration is going down towards the center. And there is there's an X component and a Y component to the centripetal acceleration. If we look at the force, you'll see it's a centripetal force. The force is in the same position as the acceleration. Remember, force equals mass times acceleration. So since mass is just a scalar, a scalar times a vector gives you a vector scaled, but in the same direction. So force is equal to mass times acceleration. The force is in the same direction as the acceleration, as shown here. Acceleration, force, acceleration, it really just changes color. Okay, now let's stop this share. Now that you've gotten that brief introduction, let's share the PowerPoint. Okay, that was, I think, where we left off last time. And now we're gonna, if you look, we ended up with V equals plus or minus square root of Km a squared minus x squared. That was the velocity as a function of position. Now you'll see that same equation appears at the top here. So now imagine a projector projecting down onto a little wheel that has a little ball attached to it, and as it goes around, it's gonna produce a sinusoidal wave, a wave that goes back and forth just like the horizontal spring. So as the ball rotates like a particle in uniform circular motion, the ball's shadow on the screen moves back and forth with simple harmonic motion. Now we're going to take that square root of Km and pull it out of the square root. So in this case, C is equal to the square root of Km, but really it's just a multiplier. It's just a factor here. Now we're gonna let's think about this V equals, or let's suspend this and go on and look at another definition of sine. V equals V0 times sine of theta. So sure enough, if we see this V0, we see that it's reduced by a sine theta term. The orange V is smaller than the red V sub 0. So V is equal to the V0 times the sine of theta, because notice how they have theta drawn here. The V is opposite that particular theta. but notice how that theta is the same as the theta that's at the center of the center of the circle. So sine okay, so sine theta equals V over V0, and you can see that if you look at the theta, V being the side opposite and V0 being the hypotenuse. Now let's look at a different sine theta, and you can see that the x component, or the x is the horizontal component. The side opposite is that square root of a squared minus x squared, and divided by a is the hypotenuse. A is the hypotenuse. So by the definition, sine theta, it's opposite over hypotenuse. Well, the opposite is the square root of a squared minus x squared, and the hypotenuse is a. So now if sine theta is equal to v divided by v0, and sine theta is also equal to the square root of a squared minus x squared divided by a, then we can equate those two. V over v0 is equal to a squared minus x squared over a. And if we solve for v, we see that it's v0 over a times the square root of a squared minus x squared. But that's, I wish it wouldn't have gone through all those equations. See, in the last one, we had v equals that c, that constant that we pulled out. We have the same thing here. That v0 over a becomes the c, the constant. You can see that they're similar. Now here's an example of rotational motion. The piston pushes this back and forth motion from the piston, and it turns it into circular motion on the railroad wheel. And there you see other examples of that if you just take the time to observe. So let's look at V0 is equal to 2 pi a over t, where t is the period. So the velocity V0 is 2 pi a is the max. I mean, that's the 2 pi a is the one trip around the circle. So it's the perimeter. 2 pi a is the perimeter of the circle. T is the amount of time that it takes to do it. So V0 is equal to the perimeter divided by the time. That's just the definition of velocity, the distance divided by time, the distance being the circumference 2 pi a divided by the time t. So t is equal to 2 pi a divided by V0. Now we have that the spring potential energy, if you pull A to its maximum extent, you have a spring potential energy of 1/2 k a squared, where a is the maximum x that you pull it. And you have the kinetic energy of 1/2 mv0 squared. That's its fastest that it's going to go. So you going from full potential energy to full kinetic energy. 1/2 ka squared equals 1/2 mv0 squared. So if we divide both sides by v0 squared, we get a squared over v squared. And if we divide both sides by k, we have a squared over v0 squared is m divided by k. Now we take the square root of both sides to get a over v0, and you end up with this equals the square root of m over k. So the period t, now look, the period t is 2 pi times the square root of m over k. You can look at that that t, the av, the a over v0 in the equation up at top, t equals pi over a over v0. Well, if a over v0 equals square root of m over k, then t equals the 2 pi times the square root of m over k. That's just a simple substitution. Now the frequency is equal to 1 over the period. And the frequency is equal to, we're just, since the frequency is the reciprocal of the period, we take this t equal 2 pi over square root of mk, invert it, and we get 1 over 2 pi times the square root of k over m. And omega, what we call the angular frequency, is equal to 2 pi times the frequency, 2 pi f, and that's equal to just the square root of k over m. Okay, and that's it for that section. It probably ended up longer than I wanted to, but that's okay.